So we'll continue today with our discussion on error control coding, and today specifically we'll try to get some feel about some subtle issues in the design of a special class of error control codes. That's the family of linear block cyclic codes, because many popular codes belong to this family, and in the process we'll have a somewhat different form of Hamming code as an example. I shall leave the example incomplete so that you try out some calculations and come out with complete encoding and decoding of Hamming code, which is a short code. Now, so the topic to start with is linear algebra over finite fields. Linear algebra over finite fields, I mean, is a very important area in mathematics, okay, where the elements or the numbers, so to say, they are defined over some finite field, and those finite fields are indicated in this form of GF within bracket 2 to the power m. GF stands for Galois field. This means that this field of mathematics or algebra contains 2 to the power m number of elements, in contrast to our usual decimal field, where it's not a finite field really. You can imagine any number, and you can it's not bounded that way. So it's a field which has got only finite number of elements. For example, m here is an integer. In the simplest form, say m may be 1. So you can define a finite field of 2 elements, which is nothing but your usual binary field with elements 0 and 1. Usually we indicate the elements 2 to the power m elements of a Galois field in this form: 0, 1, alpha, alpha square, etc., up to alpha to the power 2 to the power m minus 1. Yeah, I mean, I'll not go into the precise definition of field. Field means first a set of elements, and then the operations which should be defined fundamentally, so that you get a complete idea about the algebra, okay, where the elements are defined and it's a set of elements with certain operations. The operations, usual operations that are carried out in a finite field, are known as or named as, okay, as addition operation and multiplication operation, okay. And for a field specifically, this addition operation has its inverse operation of subtraction, if we call that inverse addition operation or subtraction. The multiplication operation also has its inverse operation of, if we call, a division operation, except that there is one small exception, that division operation is not the inverse operation of multiplication so far as this element 0 is concerned. In fact, these two elements 0 and 1 will appear in any field, any finite field, okay, as the first two elements sort of, because they represent some identity element. Like in our usual sense, 0 happens to be the identity element for addition. So in a finite field also, this symbol 0 is used to indicate the identity operation, okay, identity element over addition operation, and 1 is the identity element for multiplication operation. So with these operations of addition, multiplication, and some very obvious properties of associativity, commutativity, etc., a field is ultimately defined. So you know what kind of manipulations are possible over which elements, okay. So that's what is a field in summary. Now, so there will be elements up to alpha to the power 2 to the power m minus 2. The next element, if I go on writing, is alpha to the power 2 to the power m minus 1, which is 1. So we can say the field is closed, okay. Alpha to the power 2m is alpha, alpha to the power 2 to the power m plus 1 is alpha square, and like that, okay. So if alpha square is nothing but alpha into alpha, then this exponent may have any integer value, but that alpha to the power large integer exponent can always be folded back into one of these elements, okay.
So what exactly is alpha?
Alpha is a simple notation to indicate an element in this field.
What do you mean by element in the field? So like you find field as like complex set of operations and
So the field, I mean, consists of a set of elements which are somewhat equivalent to numbers. Okay. So in a field you can call that these are as if the numbers. Okay. So I have to represent the numbers. So I don't want to use the convention of 1, 2, 3, 4, 5, 6 because then we may confuse in our operations. When it comes to adding 5 plus 6, we will always write 11 perhaps and we will be making mistake. So I am introducing a different set of notations here for the elements. Okay.
those elements 0 and 1 has always to be
These two elements we retain because that tell us that these are the identity elements. 0 is the identity element over the addition operation which is defined in this field, and 1 is the identity element for multiplication operation. Okay. Galois field is always a finite field. That means the number of elements will be finite, which again means any integer exponent of this element alpha does not mean an element which is not covered really. There is an equivalent member of that number in this restricted list of elements. So his point is, in this expression we cannot express 0 element as some exponent of alpha, integer exponent of alpha. It is not necessary because that is a special element of addition operation. We get 1 alpha, alpha square, etc. You do not get 0, you do not get back 0. Okay, because this multiplication operation does not have its inverse operation with reference with respect to this 0 really. But if you want to bring in the notion of alpha, some authors choose to indicate 0 as alpha to the power minus infinity kind of thing. It is not necessary as such. Okay. Now, this kind of finite field is used extensively in the design of many or powerful and useful block and especially cyclic codes. Okay, that's the reason I thought I'll just mention about this field here. We will not discuss about all those codes really. And there again, usually the decoding operation is more involved. It needs more attention than the encoding operation. Okay. But the point is, one has to really specify the encoding operation very specifically, so that the properties that we discussed last time, they are valid really. Okay, encoding operation is unambiguous. You always get a specific encoder output which is unambiguous, one-to-one mapping, etc. And the same encoding operation will be known at the decoder end. Okay, but it is this encoding strategy which makes one code different from another one. For example, when you say we will discuss briefly about Hamming code, what I mean essentially is that the encoding strategy for a Hamming code I will discuss, and once that is known, the decoding operation has to be explored as and when necessary. For Hamming code it may not be necessary, these things are very structured really. For many other larger codes, one has to find out what should be the decoding algorithm and what should be the corresponding complexity and many other issues. Fine. In general, decoding is more involved. We can also guess it intuitively because it is at the decoder end, at the input to the decoder, that we will get an error corrupted code word, error corrupted word or group of n bits. If you just think a little bit, at the encoder end there is no issue of uncertainty etc. due to error. Errors come in between in the discrete channel, okay, and so at the decoder we have to find out of many possibilities which one is the best possible guess. So the operation intuitively is involved, and actually so for larger length codes it is the decoder which consumes much of the complexity compared to the encoding operation. Okay. Now again, so when it comes to the discussion of error control coding, after initial discussion of the encoding strategy, the attention invariably goes into the decoding mechanism. That there is a popular scheme of family of decoding scheme, I mean type of decoding scheme which is known as syndrome decoding scheme, which again is extensively used for decoding linear block cyclic codes. Now the Hamming code that we will discuss will put, I shall put it in the form of a cyclic code. Okay, so this syndrome decoding, which I will just briefly mention, you will try to apply for decoding the Hamming code. Okay. We discussed briefly in the last class really. The cyclic code simply means that if you have a valid code word, okay, of n bits or so, if you go for a cyclic end around shifting by one position or two position or any position, you get another valid code word. Okay, this we try to choose cyclic code primarily because theory of as well as understanding of cyclic codes is relatively easier rather than a non-cyclic code of large length. Second reason is that when it comes to implementation, hardware implementation, the cyclic codes can be generated by using some kind of shift register with feedback mechanism and other things. So, in terms of understanding, theory building as well as practical implementation, cyclic codes have some advantages. So, if you have two contending codes, one is cyclic, the other one is non-cyclic, giving similar performance, you should better choose the cyclic one.
So, but for cyclic code, it is necessary that the number of alphabets for an n-bit code word 2 is to power n. Then make free. If you have anything less than that, you can't have a cyclic code.
You can have. There are several ways of changing the structure of the cyclic code. Really, one can get what is known as a shortened cyclic code and things like that. Okay. Now, so this kind of linear block cyclic codes, they are often described in terms of a specific polynomial, which is known as the generator polynomial. Okay, and once the generator polynomial is specified, the code encoding strategy is specified. Okay, so the generator polynomial plays a crucial role in the definition of the encoding strategy, and it also plays an important role in the decoding process as well. I am writing a general expression for the generator polynomial g of x, that is one popular notation, which is summation of gi x to the power I varying from 0 to n minus k. So, I am telling that the degree of this generator polynomial is n minus k. I hope you remember what is n, what is k. Okay. Now, again for simplicity, we are assuming that we are considering only binary codes, and in that case these GIs, these coefficients, they are either 0 or 1 in the Galois field with two elements. X in this expression as well as in the subsequent ones that I will mention, it represents, it is written at the bottom, it represents unit delay or its inverse. Okay. Inverse you need not worry much really at the moment. Okay. X for the time being represents 1 unit delay. Okay. So, if I have got say G1 and then if I say G1x, I mean G1 is obtained after 1 unit delay, which may correspond to after 1 clock pulse in the hardware circuitry. Yes, in the connection polynomial for the random sequence generator. X is an indeterminate. We will talk about some polynomials, but we will not try to solve x in contrast to usual algebra. Okay. The next polynomial which I would like to define is a message polynomial. You have a group of k bits as a message. Okay. So, I would like to represent it as a polynomial mx. In a similar style, summation of mi x to the power I varying from 0 to k minus 1, because you have a group of k bits of message. And then a code word polynomial I can now define. The code word polynomial represents that code word of n bits after encoding is done. So, Cx I write as Ci x to the power I varying from 0 to n minus 1, because n is the block length. Okay. We had group of k bits, we encoded it to give get n bits with adding or putting some additional bits of n minus k. Yes, please.
So, for Gx, sir,
yes.
not significantly from 0 to n minus k minus 1.
Because you have n minus k number of parity bits in excess of k bits.
Gx is a generator polynomial. Okay. There is another polynomial which is also considered in some context, which is known as a parity check polynomial, Hx. Okay. Fine. So, we are not talking about a parity check polynomial, we are talking about a generator polynomial. So, its degree is n minus k, we will see that later. Its degree is n minus k, okay, but it will have n minus k plus 1 coefficients.
So, do we need to define Gi, Mi and Ci separately? So because like actually if you see the only two of them are independent. The third one will depend upon.
Which one are independent?
I'm saying of these three. So the questions we've defined.
Right.
What I'm saying is that I think we don't need to define all three independently, because at the most only two can be independent. Third has to depend upon them. Like if we get a generator to polynomial and a message polynomial,
Right.
the code polynomial is a combination of those two.
Yeah, like that. So your point is, I mean, what is the starting point, perhaps, isn't it? The starting point is that you have to think, why are you designing an error control code for some application, okay? And usually the application environment will tell you some other constraints, like especially because you will add a few more bits. So there may be a constraint in transmission bandwidth, which will mean that the code rate should not be higher than this. Okay. So you have to, that may be a fundamental constraint, which is a ratio of k and n. So now you will have to find which ratio will be suitable. I mean, you have to find a ratio first of all within the restriction really, and then find the values of k and n, and we will find that if the larger value of n can be accepted, it is better, but with larger value of n, no, the ratio may still be same. I can achieve a ratio of 0.8 as that of k by n by considering a larger value of n and larger value of k. Okay. But the point is that with a larger value of n, usually the number of operations that will be necessary in the decoder again shoots up. Okay. So if you really try your hand in encoding and decoding, you will find that again there is some indirect restriction on n, but anyway that is not the point at this moment really. Our point is that if the code rate is given, we will expect that either k or n is known, and then it is obvious that if n is known, I know the value of k. So as you said rightly, two of the parameters will be known and one will be free at the most. Okay. In general, even both the two known parameters also may not be known very exactly. It depends on the application. Yes, please.
We take a code word and that would consist of n bits.
Yes.
This code word is split into the message and the
Parity part and the systematic part. Yes.
when we are already having a code word polynomial, then why do we want to go for these individual generator polynomials and message polynomials?
Your question is, when we have a code word
Yeah, for the entire n bits.
for the entire n bits, then why do we go for this separate one? In fact, today we are trying to give a somewhat algebraic structure to this issue of coding and decoding, encoding and decoding. So I do not have the code word available. I do not have the code word available. Okay. What I am assuming is that I have to encode a group of k bits to give n bits. K and n have been decided by some reasons really. Let us not worry much about that. Today what I am trying to establish is how I should encode, what should be the encoding strategy. Okay, I am more focused about that, and it is only after encoding that you get a group of n bits, is it not? How do you generate those additional bits in the systematic form, n minus k bits? That strategy has to be decided. Okay. This generator polynomial, as I was telling you, is a characteristic of a code. So for a Hamming code, we expect one form of generator polynomial. For some other code like BCH code, okay, we expect a different form of the generator polynomial. For Reed-Solomon code, a still different form of generator polynomial. Okay, that's a non-binary code anyway. So I just introduce the polynomials here. Can I also write a polynomial description for the received word? The received word, if n bits are transmitted from the transmitter, I expect the n bits to be received somewhere at the output of the discrete channel, so that I can accept a group of n bits to the decoder. So at the input to the decoder in the receiver chain, okay, I can write the input in a polynomial form, a group of n received bits as summation of ri x to the power I varying from 0 to n minus 1. Okay. And because the code is binary, these ri's also have to be binary really. So I must receive either 1 or 0, nothing different. Now we know that there will be errors in the channel, and hence let us define an error polynomial also, e of x, which is summation of ei x to the power I equal to from 0, I varying from 0 to n minus 1. So what I am doing is I am also trying to visualize that error pattern really. okay, and these EIs again will be elements of Galois field 2, and we can guess that usually most of these EIs will be zeros. That means, if I have received a group of n bits, then error may be there at one or two places or only a few places. So, at other places there should not be any error, and hence, and each place is dictated by the corresponding value of corresponding x to the power I. I here indicates the place, the bit location really. So, we can say that usually most of these EIs will be 0, okay. And the what should the decoder do? The decoder will receive a block of n bits, which I am calling as a received code, received word, okay. And then from this group of n bits, it has to do some decoding operation and give me back my transmitted message polynomial mx, okay. So, I am just writing an expression for the error polynomial. Then I have written this sort of identity, that the received word is nothing but the summation. This notation here I have made explicit is the XOR operation, when you define a code over Galois field 2. When I was talking about the addition and multiplication operations, the addition operation reduces to the XOR operation, okay. So, R of x, the received word, is nothing but the transmitted code word added with the error word or error polynomial. So, Rx is Cx plus Ex. Is that acceptable? So, what I am trying to say is that the transmitted code word was transmitted one bit after that, okay, bit by bit, and in the process, in the discrete channel, okay, occasionally errors got added. So, I got the received group of n bits where errors EIs on some locations may be 1, and in the locations where there was no error, EIs will be 0, okay. So, the received polynomial is nothing but the summation operation. Summation in this case specifically is the XOR operation of Cx and Ex, okay.
This XOR is for
Bitwise XOR, bitwise XOR, because if you really think a little bit about what I meant by x and indeterminate, okay, x is an indeterminate. So, if I have to add two polynomials of Cx and Ex, okay, both of which have the same degree of n minus 1, then addition has to be bit by bit, okay. So, as if you have stored, if say Cx is known, Ex is known, they are both stored in an n bit register, and XOR them bit by bit, you get Rx, something like that really. So, XORing is bit by bit operation.
So the RS that we get here is free of errors.
No, that depends on the error polynomial. That is what I said, the received word Rx, that means the received block of n bits is nothing but the transmitted block of n bits plus the error block of n bits. Yes, please.
What is the summation of the signal means?
What is the summation of?
Signals means like if error is.
I am not talking about a signal today. I am talking about some word and polynomial.
So the bits. Okay, bits.
One at a time. Yes.
So code word has a bits 1010 like this.
Right. So that bit sequence today I am expressing in the form of a polynomial.
Bitwise they are sorted.
So,
To get this.
so suppose I have a polynomial ax defined as ai x to the power I varying from 0 to n minus n minus 1, and another polynomial b of x, which is summation of bi x to the power I is from 0 to n minus 1, and when I say I am adding two polynomials ax and bx, what I mean is it's summation of ai XOR bi x to the power I varying from 0 to n minus 1. That means I am talking about the bit by bit XORing at the same position. If ai is stored in this register of length n, a0, a1, a2 up to an minus 1, and bi is stored here in this register of same length b0, b1, b2, etc., bn minus 1. This both are of the same length because the polynomials are of the same degree. Okay. Then I am talking about XOR operation in a bit by bit position.
So I want to ask that if the error bit A1 is 1 and also B1 is 1, then the C1 becomes 0.
0. That means the bit gets inverted, na? See, when if you had transmitted 1, but an error occurred, then this 1 will appear as 0 at the receiver. Does it go by the common sense? You are transmitting 1, okay, there was an error, okay, that means ei corresponding ei was 1, so they get XORed, you get 0. You know that XOR can be used as inverter, isn't it? Similar to that basically. If the bit was information bit was 1, I mean the coded bit was 1, that gets inverted really. Yes, there was another question.
Represents at ith delay, what was the information stored? What was the information?
Your question is on the polynomial. The polynomial here indicates is used for an alternative form of a sequence of bits of finite length, of length n or k or something of finite length.
We are checking at the ith unit delay. What is the
So in this polynomial expression, I am considering the whole group of bits really.
at ith position? What is the cost?
I am using as an integer which takes a value from 0 to n minus k. So if you consider gx explicitly, this means, let me try to write here gx, say the first polynomial that I defined. Yeah, its summation of gi xi is g naught plus xi to the power x to the power 0. We consider that to be 1 really. Okay, so it's g naught plus g1 x plus g2 x square and like this, g n minus k x to the power n minus k. This is the full form, isn't it?
G1x is after one delay.
Yeah. So if I am talking about generating gx, okay, and observing it one after another, then the first thing that I will observe is g naught, and then in the next clock, as if I will observe g1. So there is a delay of 1 unit. Then after one more clock, I will observe g2 and like that.
So then shouldn't it be after n clocks? It shouldn't be g and n minus k. After k clock, g n minus k, k x. We are observing after k clocks. What is it? X to the power k.
Okay. So your question is why I am writing x to the power some integer j rather than jx. Is that a question? His question is why I am writing x to the power j to indicate j units of delay rather than jx. It's a good question really. This again is a notation we follow. Okay, we do not write jx because then j will appear as a coefficient of x. Okay, whereas we used to use some other the bits in form code word bits or message bits as the coefficients of x. So by notation, x to the power j indicates j unit delays. It usually indicates, and we use x to the power j rather than jx. Is that okay? Any other questions?
Say in the previous question,
Yeah.
when 1 was 0 and the result is 0, is the, we are assuming that the error is negative polarity, opposite polarity to that of standard traces.
No, I did not assume anything about the polarity of the error really. What? So you transmitted a binary 1, okay, and error occurred. So error may have two possibilities: either error occurred or it did not occur, because we are talking about a binary channel. Our coding decoding scheme is also binary. Okay, so when you said error occurred, that means the corresponding ei, as per my notation, I am calling as 1. Okay, and what I said is that let this 1 be XORed with the corresponding message bits, the code word bits. Okay, XORing results in inversion, and that's what is the effect of error. You had transmitted one error, one high pulse. Okay, because of error that was detected somewhere in the receiver as 0, logic 0. So we say there has been an error.
Sir,
Yes, please.
it's the same scheme for the parallel data transfer.
Parallel.
Data transfer.
we are
We are considering serial data, one bit.
yes, yes,
If there are multiple bits, then
okay, okay.
at a one instant, whatever we are getting,
Right.
that will represent our whole process.
Parallel data can be viewed in multiple ways. One way would be that if you decide, you can also define a non-binary code there. Say parallel group of 4 bits will mean there will be 16 possibilities in one go. Okay, so one can define a non-binary code. Okay, over an extension field, as they call it, extension Galois field, but we don't want to discuss that basically. The other way out is that let there be parallel data from a data source, you multiplex them, put them in a serial form so that it appears as a binary serial stream, apply a binary coding there, coding decoding, and again before you deliver ultimately to the information sink, you convert them from serial to parallel fashion.
But is it very necessary that we always have a error scheme for only serial data, not for parallel data?
It's not necessary, but again when it comes to the design, you usually binary codes are favored, they are less complex, so to say. Okay, so many of the popular codes are binary in nature, though there are
Even the parallel data is a binary code, but at a
another way would be that if you show like really, if there are 4 parallel paths, okay, in each path you may like to add, each path see individually is a binary output stream, data serial stream, so you use one coder, encoder 1, another encoder 2, maybe identical similar one for path 2, and like that, though that will unnecessarily be costly perhaps. So these are these are the details to be seen before you actually design it in hardware. Okay. Yes, please. No, because we are not saying error polynomial may be anything. My only point here is that if n bits were transmitted, I receive n bits, and say each bit has, there is a provision in Ex that each bit may be in error, or there may not be any error, or there may be any combination of error. How it has actually appeared, it has actually happened. Okay, if you try to imagine how it happened, how there were 3 errors or 5 errors, you have to get back to the physical process, maybe all the channels you will have to understand, all the detection demodulation schemes you will have to understand. We are not doing that at the moment. Today we are talking about, I mean, okay, certain number of errors have occurred, and so long as this number is within the restricted range of t, if you remember, we talked about t as error correcting capability, the decoder must correct all of them. Okay. Yes. Received what?
Can't it be a polynomial like Rx is defined in the string?
See, Rx is a polynomial. We are calling this as a received word polynomial. That polynomial I am not writing, but everywhere it is understood. The expression is that of a polynomial, so it is a received word polynomial, error polynomial, message polynomial. The polynomial word is implicit here. Okay. I avoided writing calling this as received code word. Okay, that Cx I said transmitted code word to be a code word to be transmitted. This one truly speaking may not be viewed as a word because this is already contaminated with error, and this is not a valid code word really. If there is an error, then Rx is not a valid code word if you think. Okay, and that's why I am not writing code word, but it is a polynomial after all. Yes.
Message polynomial, so summation from I equal to 0 to k minus 1. So we can view it as some polynomial representation of the k bit message word.
Yes.
So how can we view the generated polynomial, sir, because it is summed from 0 to n minus k.
Yes.
So, but n minus k is the number of means parity bits of k.
Right.
So then it should be, sir, the actual number is n minus k. It should be 0 to n minus k.
Again, see, let me allow me to go further really. Okay, that's why this gx polynomial I am calling as the generated polynomial. It helps in generating code word once you give me the message word. Okay, how does it do that? Let us go further and see. A general encoding rule which is applicable for linear cyclic codes is simple as this. Cx, the code word polynomial, in many cases is nothing but the multiplication of the message polynomial and the generated polynomial. Yes, the question. Yes, the issue is the multiplication operation. This by this multiplication operation, I mean the multiplication operation as per the definition of the field here. Okay, as per the definition of the field. This is a polynomial multiplication. Polynomial multiplication. Okay, I shall briefly tell you that this multiplication involves a modulo operation. Okay, we will come back to this when we consider the example of Hamming code. Yes. Yes. All the coefficients will always be XOR because that's the addition operation. For multiplication, depending on the cases, a polynomial modulo operation has to be done. Yes. See, in this case, the problem does not arise. If you just check, the degree of mx is how much? K minus 1. Is it not? Degree of k minus 1. What is the degree of gx? N minus k. Then what is the degree of the overall polynomial? N minus 1, isn't it? So this polynomial goes straight away. Like usual polynomial, okay, only when the coefficients they are to be multiplied, okay, and added, one has to go to the field operations of addition and multiplication. Okay, like for 2-bit Galois field, that is GF2, the multiplication reduces to an AND operation. AI into BI will be ANDed operation of that, specifically for GF2.
For a particular coefficient of xi,
Yes.
something as ai not bi.
Yes.
Plus
AI plus 1 into BI minus 1. Okay. First carry out AI into BI, which is by ANDing operation, and similarly AI minus 1 in AI plus 1 into BI minus 1, and then XOR both the outputs. Okay. So one popular encoding scheme is straight away multiplication, polynomial multiplication within the definition of that finite field of the message polynomial with the generated polynomial. Okay. So given the message polynomial, you multiply it with the generated polynomial, which is the characteristic feature of that particular code. So if you are going for Hamming code, I shall give you one particular generated polynomial. So take any message polynomial, multiply it with by the same gx, you get the corresponding code one. Okay. What is very obvious here is, yes, please.
Gi, you told that these belong to Galois field of 2.
Yes.
Limit of 2 is containing 0 or 1.
Yes, Galois field, it has got 0 and 1. Yes.
All these coefficients G0 to 3.
Some of them will be 0, some of them will be 1s. Okay. For example, let me here itself give you an example of Gx for the 7-4 Hamming code. Gx for 7-4 Hamming code is x cube plus x plus 1. Is one form of Hamming code which I thought I would tell you. What is the degree of Gx? You tell me quickly what is G0, what is G1, what is G2, what is G3? G0 1, G1 1, G2 0, G3. Okay, so Gi is maybe 0 or 1. Fine. Okay. What is the degree of Gx is 3. So we know n minus k is 3. Okay. Let me tell you that n is 7. Yes, which incidentally is 2 to the power 3 minus 1. Okay. So n is 7. So what is k? 4, isn't it? So here is a code, Hamming code. What does it do? It accepts a group of 4 bits, 4 information bits or message bits, encodes it to give you 7 bits. Okay, to give you a code word of 7 bits. Fine. This particular code we indicate in general in this form n comma k. Sometimes we also put t. Let's not consider that. N comma k code. Okay, n comma k Hamming code, which is 7 comma 4 Hamming code. So if I am talking about 7-4 Hamming code, and I tell you that okay, consider this Gx of x cube plus x plus 1, I have told you the features of the encoder. Okay. Then you also know how to get the corresponding code word. What you are going to do is that if I give you now a block of 4 bits, you should be able to give me the Cx by multiplication, polynomial multiplication. Okay. Yes.
Multiplication is polynomial multiplication. Something like that. The original polynomial may have coefficients not 0 and 1 equals 2.
It cannot have 2 is equal to 0. The coefficient 2 is equal to 0 because it's a binary XOR operation. No? Addition of the coefficients will somewhere. Okay. Fine. Is it a systematic code or non-systematic code? Non-systematic, isn't it? Because the message positions, they will get changed because of after multiplication with the gx. Fine. This same code can be put in an equivalent systematic form as well. This code incidentally can correct single error. So, if you remember our T, the way we defined in the last class, the number of errors that can be corrected, T happens to be 1 for this 7,4 Hamming code, and we also indicate this as 7,4,1 Hamming code, telling you that 4 message bits can be encoded to give 7 bits, and the decoder will correct 1 error, definitely. Okay. I'll come back to that. I'll come back to that. Error is 1. It can correct 1 error. 1 error. After multiplication, you will for the same index of I, same exponent of I, you will go for XOR operation, the addition operation. Yes.
So if you multiply these two polynomials, so the negative aspect is that
If there is one error in mx,
yes, sir.
better to say that if there is one error in cx.
No, sir, what I'm saying is one error in either mx or gx. It will manifest as multiple errors in cx because I'm multiplying the thing.
So I am not fundamentally worried whether the error is in gx. Gx is a code identifying polynomial. Okay, what will be transmitted is cx. So you simply say whether there is one error in cx or more number of errors in cx. Errors will be in Rx. So errors get added with Cx to give you an Rx, which will be different from Cx. Yes. We'll try that out through the example later on. Okay. So the encoding rule in the simple form was a direct multiplication of two polynomials. Okay. Here is an equivalent form. It may be more desirable because it is in a systematic form. Though in terms of power, error correction capability, etc., both are same. Okay. In this expression, I have introduced an expression like this. You can look at this. This is known as read as the remainder polynomial when a polynomial ax is divided by the polynomial gx. Rax is the remainder polynomial when ax is divided by gx. Okay. So I am calling the new looking code word as C prime x. I have put it in a manner wherein I have done some operation on mx first. If you look at the first term, this term, what I have done is I have multiplied mx with x to the power n minus k. Can you tell me what does it mean physically?
Shifting it
I have shifted the message polynomial by n minus k positions. Okay, as if in a shift register. Then what I have done? So if I now, if my whatever mx was given to me in the polynomial form, now the index of x will increase by n minus k. Is it not? That's the only change. Now I am dividing that shifted version of mx by the generator polynomial gx, and after division I may get some remainder. Whatever is the remainder, I am calling that as the second term. Okay. This plus here incidentally is the XOR operation. Okay. So I am adding that remainder polynomial with the shifted version of the message polynomial. Okay. For binary Galois field 2, you better read this as subtracting. for GF2, okay, subtraction is the same operation as that of addition, XORing operation. Think of this. Okay, so fundamentally what is to be done is that a shifted version of mx is first written, and then that shifted version is divided by the generated polynomial. Whatever is the remainder is now subtracted from this shifted version of mx. Now once I subtract that remainder, is it not a fact that this whole thing I can write equivalently as some multiple of mx? It is something like, numerically, okay, I am writing 15 as 17 minus remainder of 17 when divided by 5. Suppose please see, is it not is there any mathematically any problem? 17 I am writing as 17 minus remainder of 17 when I am dividing by some element, some number 5. Okay, so 15 can be written at that way. So it is somewhat similar to that. Basically what I have done is a shifted version of mx, it was not multiple of gx in general. So I am forcing this whole thing to be a multiple of gx, because fundamentally the encoding rule says that any code word is divisible by the generator polynomial. Any code word in the encoding of this kind of linear cyclic code, block codes, is always divisible by the generator polynomial. That is why I could write the encoding rule as a straightaway multiplication of the generator message polynomial with the generator polynomial, so that the code word polynomial is always divisible by gx. There won't be any remainder. So this is a strategy for encoding cyclic linear block codes. C prime x is an equivalent form of the code word, is different in structure from Cx, but Cx was non-systematic. C prime x is in a systematic form. See, what I have done is I have done a trick basically. I have shifted the message polynomial in one side, and then from this portion actually I am adding the parity bits there, so that this in this code word, if I now look, I will find the message bits at one place, and then will come the parity bits. Mathematically it means that you shift the message polynomial, then divide that shifted message polynomial by the generated polynomial, subtract it from the shifted version, so that after subtraction this whole thing now is divisible by mx by gx. This whole thing now is divisible by gx. Yes. No, it is a fundamental property of feature of the encoding rule. Any code word will be divisible by the generator polynomial. The earlier code words was divisible by generator polynomial gx, because it was theta mx into gx. Okay, so now also I am ensuring that the code word is still divisible by gx. Okay, though here it will look different because I have shifted the message in one portion. So this is also divisible by gx, and I can put it as some m prime x times gx, where m prime x is, to show that this is again divisible by gx, I am writing it in this form, where m prime is not the message polynomial. The message polynomial was mx, but after this operation I have ensured that you will have the message in one portion, and the whole code word will be divisible by the generator polynomial. Okay. Because I first divided this shifted version of mx by generated polynomial, I found the remainder. This portion was the remainder. I subtracted that remainder from the x to the power n minus k into mx. So after subtraction, the whole thing has to be divisible by gx. Just think a little bit. So I divided some number with a number, and then there was a remainder. So I am subtracting this number from the original number. So now there should not be any remainder. It should be fully divisible. Okay. So any code word is divisible by the generated polynomial. For decoding, what we do is a very important step, starting point for the decoding is that whatever we receive as Rx, the received polynomial, we divide it by Gx, notionally, conceptually. Okay. If I divide by Gx, I get a very interesting remainder. We know Rx, the received code word, is the sum of the sum is that XOR sum of the code word and the error polynomial, code polynomial and the error polynomial. And just now we said any code word is a multiple of Gx, is divisible by Gx. So when I find the remainder, when Rx is divided by Gx, I find I get a remainder due to error polynomial only. So this remainder is something interesting which is not dependent on the message polynomial. Just think a little bit. Yes. Yes, that's what I said. You write minus here, okay, to be subtracted, but for binary field, actually plus and minus, they are equivalent operations. Think of that. You people are masters of Boolean algebra and logic here. Okay. For binary coding, addition is equivalent to subtraction. Okay. So this remainder polynomial is something which is independent of the Cx or the message polynomial. We will start from this point.
12 with 3.
Pardon? I'm not talking about total XOR, I am talking about XORing of the coefficient. See, when I say you are subtracting one polynomial from the other polynomial. So subtraction will occur only at the respective positions where you have got the same exponent of x here and here. There won't be any carry. Take a small problem on this. I mean, small illustrative examples in the next class. Then, okay. Usually, there you have to add XOR the corresponding coefficients for the same exponent of x. Okay, and there 1 plus 1 plus means XOR addition is 0. 1 minus 1 is also 0.
That's so what I'm saying is that the remainder in this case k bits, last minus k bits.
No, because this is a shifted version of mx.
So the remainder won't be in those.
The remainders will have a degree less than that of gx, and hence they will appear after this first term. We'll start from this point once again. Think a little bit about this. Thank you very much.